For our first method of keeping track of polynomial multiplication, I want us to think back to when we were first learning about multiplication. And one of the ways that we understood multiplication is as representing an array of things, right? 6 bananas times 5 was an array of 6 bananas in a row, 5 rows like that. And from there, we generalized to say, okay, we can have an array of little boxes, and multiplication describes the area of a rectangle. In order to help us keep track of multiplying polynomials, we're going to think of each polynomial as representing the sides of a rectangle, and then their product, the result of multiplying them, gives that rectangle's area. And that's what I've drawn a picture of here. So we have this rectangle. Its top has length 3x squared plus 5x plus 4, and its side has length 2x squared plus 6x plus 3. And so this area, whatever it is the product. Okay, but how does that help us? Well, we can say, I'm going to take this rectangle and I'm going to cut it up into a bunch of little rectangles. So I'm going to slice it like this so that I have a rectangle whose top has length 3x squared, one whose top has length 5x, and one whose top has length 4. And then I'm going to slice it like this. And now I have a little rectangle whose side has length 2x squared, another little rectangle whose side has length 6x, and one more whose side has length 3. And the big rectangle is the sum of the little rectangles. And finally, the area of each little rectangle is the product of two monomials. So this rectangle has width 3x squared and height 2x squared. So its area is 6x to the 4th. This little rectangle has width 5x and height 2x squared. So its area is 10x to the 3rd. This rectangle has width 4 and height 2x squared. So its area is 8x squared. This rectangle has width 3x squared and height 6x. So its area is 18x to the 3rd. This little rectangle has width 5x and height 6x. So its area is 30x squared. This little rectangle has width 4 and height 6x. So its area is 24x. Width 3x squared, height 3, area 9x squared. Width 5x, height 3, area 15x. Width 4, height 3, area 12. And there we go. Our product of polynomials understood as the sum of the little rectangles. So we'll have 6x to the 4th plus 10x to the 3rd plus 18x to the 3rd plus 8x squared plus 30x squared plus 9x squared plus 24x plus 15x plus 12. And notice that I just went through and copied this in such a way that my like terms are next to each other. I found that my like terms lived along these top left to bottom right diagonals. Fancy term for those is the anti-diagonals. But my like terms all lined up nicely like that, which made them easy to find. That won't always happen. It'll happen if we're multiplying polynomials written in descending order that have all of the powers of x present. So it'll happen if we're multiplying nice enough polynomials. It happens often enough to look out for it. Our last step, of course, will combine the like terms. We have 6x to the fourth. 10 plus 18 is 28. X to the third. 8 plus 30 plus 9 is 47. X squared. 24 plus 15 is 39x, and then plus 12. And there we go. Now in that example, I chose those polynomials so that all of the side lengths were positive numbers, which we can imagine having some sort of geometric reality. Sometimes we'll have some sides of our rectangle that we label with negative numbers. That's not real geometrically. This is really just a tool for keeping track of what we're doing here. But understanding multiplication of polynomials in this way is going to be really useful going forward. So we're going to continue with this understanding of multiplication, even when it doesn't have quite as much geometric reality. Let's see just another example of this multiplication method. So 4x plus 3y minus 6 times 3x minus 5y plus 2. I have polynomials with 3 terms each. So I'm going to make a rectangle where I can split it up into 3 rows and 3 columns. So on my graph paper here, I'm going to give myself 3 squares for each column just to make sure I have room to write. Make sure that each column has enough room for you to write, because we write horizontally. Each row is just a line on my paper. And then I'm going to write my first polynomial across the top. So 4x plus 3y minus 6. When I have subtraction, I'm going to make sure I keep the negative sign with its term. Down the side, I'll have 3x minus 5y plus 2. It doesn't matter which one you put across the top, which one you put down the side, because multiplication is commutative. And now, for each little rectangle, we'll say the top times the side. So 4x times 3x is 12x squared. 3y times 3x is 9xy. Negative 6 times 3 is negative 18x. 4x times negative 5y is negative 20xy. 3y times negative 5y is negative 15y squared. Negative 6 times negative 5y is positive 30y. 4x times 2 is positive 8x. 3y times 2 is positive 6y. Negative 6 times 2 is negative 12. Okay, so let's see where my like terms are. I've got only one x squared term. So I'll have 12x squared. I have a 9xy minus 20xy. I have a negative 15y squared. I think that's my only y squared. And then let's see, I have a negative 18x and a positive 8x. I have a positive 30y. I have a positive 6y. And I have a negative 12. And notice that as I went through there, I checked off each term as I copied it, and that lets me now look and see that I got every term. Notice that this wasn't quite as tidy as the previous one. I didn't have like terms down the anti-diagonals. So it's important that I carefully keep track of the terms to make sure I don't forget any. Now I can combine my like terms. 12x squared positive 9 plus negative 20 gives me negative 11xy. Negative 15y squared. Negative 18 plus positive 8 gives me negative 10x. Positive 30 plus positive 6 gives me positive 36y. And then I have a negative 12. So again, thinking of multiplication as representing the area of a rectangle gives us this nice way to keep track of multiplying two polynomials.